10.3 is on areas of shaded regions, and then we're going to go a step further, and we're going to find the probability that something lands in those shaded regions, okay? So it says find the area of the shaded region formed by the inscribed regular hexagon. Okay, so we've found areas of hexagons, we've found areas of circles. Now we're going to do the area of the circle minus the hexagon. So I don't care how you write this. Sometimes I kind of abbreviate it by saying like area of the circle and area of the hexagon. So maybe I write like hex or draw a little hexagon. So the area of a circle is going to be pi r squared, and in this case we can see the radius, right? So it's going to be pi times 10 squared, which is 100 pi. But the area of the hexagon we don't have. Okay, now it's nice that it's a hexagon though, because we kind of talked about this before. If you have a hexagon and you break it into its like 6 triangle shapes, these little central angle triangles. This angle right here is 60 degrees. So if I look at half of that, I end up getting a 30, 60, 90 triangle. You with me? You understand what I'm saying? We did this when we did the areas of regular polygons. And so if we know that this distance is 10, because that's the radius of the circle, and it's also the radius of the hexagon, we know that that's 10. That means that half of that side, right, which makes sense, is 5. And then the height, the apothem, do you guys remember that? What's that going to be? 5 root 3, exactly. So if I try to find the area of the hexagon, I could use 1/2 perimeter times apothem, like we learned about in that previous section. Or I could say, oh, I have 6 of these triangles, and I could find the individual triangle. 1/2 base is the side length, 10 times the apothem is our height, and then multiply by 6. Okay, you'll get the same thing. So let's say I do 1/2 PA. So 1/2, my perimeter is, each side is 10, and I have 6 of them, so 60, and my apothem is 5 root 3. So 60 times 5 is 300, and when I divide by 2, I get 150. So I'm going to write this as 150 root 3. Okay. So if I want to find the area of the shaded, that would be the entire circle, and then it's like I cut out that hexagon and I remove it, okay? So I'm going to take the area of the circle minus the area of the hexagon, so I'm going to have 100 pi minus that 150 root 3. And that's an answer. So sometimes you guys are like, well, what's the number? What's the number of the answer? That's a number. You can leave it like that. That is the most exact answer that you can have because there's no rounding that's involved. Colin, put your book away, please. All right, so the next one. So find the area of the shaded region shown below. So if I'm finding the area of the shaded region, I'm going to do the area of this big rectangle. And so how do I possibly find this area of this rectangle? Yeah, Colin, what do you think?
So you can look up inside.
Yeah, and what is this length, though?
I can't see what that number says. Oh, all right, so 16.
Yep. Do you need a notes thing somewhere? All right, Colin, what about the width? Yeah. What do you think? Any idea? Maya thinks she knows. What do you think, Maya? Yeah, so she's saying like one of this radius, there's actually 1, 2, 3, 4, 5, 6 of those radii across. So she took the radius and multiplied by 6. So she's like, oh, 8 times 6 is going to be 48. Or you could say 16 as the diameter, 16 times 3 is also 48. So I agree with that. So the area of the rectangle is going to be length times width. So 16 times 48. Did you guys do that for me? You guys are faster typers. 768, exactly. All right, now we need the area of the 3 circles. Well, how about the area of one circle? So the area of one of those circles is going to be pi times r squared. So we're going to get 64 pi. So in order to find the area of the shaded region, we need that entire rectangle, 768, and we want to subtract out 3 of those 64 pi's. So if you do 3 times 64, you end up getting 192. So this answer would be 768 minus 192 pi. And you can leave it like that. So if you want to find decimal approximations, it's fine. I would use the pi button on like the first one and the second one, right? They both have pi. So like for the first answer, if I did 100 pi minus 150 square root of 3 in my calculator, I would get a decimal approximation of 54.352. And for this one, if I do 768 minus 192 pi, I get 164.814. But you have to be kind of careful. You don't want to do what we call intermediate rounding. You don't want to round in the middle of the problem, and that's what Charlie was just asking me about. Like on some of his homework problems, he found like, you know, in the last homework we did, the area of the sector, he would do like 140 divided by 360. He'd find a decimal there, and then he would just like take that decimal times something, but he wouldn't like store that in his calculator. He would just write like 0.38. And all of his answers were off like by 4 units. And he was like, why are my answers like different than the people at my table? It's because he was rounding on that first part. Does that make sense? So just be really careful with, I've talked about you guys are building my bridges in the future. I don't want you to be off by half a mile when you're building a bridge. That would be terrible. Half a mile is significant, right? So that's what we're going to have. And then as always, we put our units. So we have centimeters squared and we have inches squared. All right. So how about this one? So find the area of the shaded region formed by the inscribed equilateral triangle. Okay, so first of all, we have the area of the circle, which I think you guys can all see. What's the area of the circle? Do you guys see that the radius is 4? Yeah, so 16 pi, that's easy. The area of the triangle, a little bit harder. Much harder, right? Are you guys trying to find it? Because some of you guys might be like, oh, well actually it's not much harder because I gave you the area of an equilateral triangle last time. Because some of you, if I didn't have the 6.8, let's say that wasn't there, some of you might be like, oh, it's going to be 4 and 4. It's not 4 and 4. That's not how it's divided. Right? It's not exactly equal on both sides. So you would have to divide this into triangles, where this would be 120. And then you'd have to divide straight down, so you get a 30, 60, 90 triangle. That's how you would have to find the area of that triangle. Now look how nice your teacher was. I didn't even know I was so nice to you guys. I was going to make you do it the hard way. What did I give you? I gave you 6.8. So that's going to at least help us. So we have 6.8 as each side. And if you remember, there was a formula for an equilateral triangle if I had 3 sides, SS and S. Do you guys remember the area of an equilateral triangle? Charlie's flipping frantically. He's trying to find it.
Hold on.
Root 3 over 4 side squared. So if you remembered that, you can use that. All right. So let's say we knew that, so we could do root 3 over 4 side squared. Otherwise, we're going to break it into like 30, 60, 90 triangles like I talked about. You could break it here for a triangle, and then this would be 60, 30, and 90. Right? So we have root 3 over 4 side squared. So I'm going to have 6.8 squared, and then so on. So that 6.8 was probably rounded. I shouldn't have done that. All right, so times, let's do divided by 4. So I get like 11.56 root 3. My general rule is if you have like a decimal point times pi or a decimal thing times a square root, I tend to just multiply them. Does that make sense why I would do that? It's like it's a decimal anyway. I might as well just multiply that number in. So let's do times root 3. That ends up being 20.0225 something. So the area that's shaded is going to be the 16 pi minus that 20.0225. Okay, which is going to be around like 30.243 centimeters squared. Okay, is this making sense so far? Yeah, so just find the area of the outer, subtract out the area of the white part, and you get the area of the shaded region. Okay, whoops. All right, we'll skip the challenge for now. Let's try the next ones. Although I really like the challenge. It's interesting. So in the challenge, it's saying a square is inscribed in a circle with a radius of 10, and it's asking you to find this area in here. All right, we're not doing it right now, but your radius of the circle is 10. You would be able to find that. All right, so let's talk about probability in general. Probability is not that hard. Okay. A probability is a number between 0 and 1. I can never have 120% probability that something's going to happen. Does that make sense? Have you ever heard someone say, oh, the probability that that's going to happen is 120%? Like, that's weird. I guess it's a hyperbole. It's like an exaggeration, right? But probability is always a number between 0 and 1. So 1 is 100%, right? Remember percent means per 100, 1.00. If I talk about 80%, you know we always write it as 0.80, right? 80% or 0.8. So a number between 0 and 1 that represents the chance that an event will occur. An event with probability of 0 cannot possibly occur. An event with probability of 1 is certain to occur. So geometric probability is the probability that involves some kind of geometric measure. So it could be a distance, it could be an area, volumes, whatever. So if we talk about the probability with length, this is kind of a weird drawing. I didn't draw it on here for you. But it says let AB be a segment that contains the segment CD between it. If K is a point and it's chosen randomly to fall anywhere on A to B. So if I'm taking my pen and I'm blindly putting it on here, I have to kind of look because I can't get it on there. And that's where my point K is. All right, what was the probability that K landed inside CD versus inside of AB? I mean, based on my picture, it looks like 1/4, but what if CD was smaller? I don't know. It's going to be whatever length this is divided by whatever length the total is, right? This makes sense? We'll do one that has numbers in a second. So let J be a region that contains region M. If I randomly choose a point K and I put it inside there, boop, like that, what's the probability that my point lands on the inside of M? Yeah, exactly. The area of M divided by the area of J. Okay, so that's what we're going to be doing. So we're going to find different areas and we're going to divide them out. So looking at this number line, so it says find the probability that a point chosen at random on CB is actually on AD. So I want to find how long AD is. So I'm going to do 1, 2, 3, 4 units, right? So it's 4 units long. And then I want to find how long CB is. So what's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 units long. So what's the probability that if I choose a point randomly that's on the entire CB, that it will be somewhere inside of AB? Yeah, it's 4 out of 10, which is indeed 2/5. Yep. Okay, that's easy enough. Do you guys understand that? It's not a hard concept. Okay. So Beanbag Game consists of 4 circular holes on a 3-foot by 4-foot board. So kind of like cornhole, but there's more holes. The circular holes have a diameter of 1 foot. So these have 1 foot here. If a beanbag is equally likely to land on any point on the target, find the probability that the beanbag goes through one of the 4 holes. Yeah?
Wait, so on the last one, it's got 11 dashes between.
Yeah, but you're counting spaces. So you're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Yeah. So don't count the, it's kind of like when you're counting like slope with a number line. Like a lot of my Algebra 1 students, if I go up like this to that point from 0, 0 to 2, 3, they want to count like, they're like 1, 2, 3, 4, but we don't count that, right? We count it as up 1, 2, 3 spaces when we count slope. All right, so we want to find the area of this whole board. So we said it was a 3-foot by 4-foot board. So our area of a rectangle is 3 by 4, which is 12. And the area of one of those circles is going to be what? A little tricky. Like pi times, like you're thinking 6 inches? Is that what you're thinking? Let's do it in feet. Yeah, you could convert everything to inches, but then you'd have to change the 3 and the 4 to inches too. Okay, so let's do 1/2. That's our r squared. I guess I should put my pi in there too. It doesn't have to be at the front, it could be on the back. So we have pi r squared. Okay, please help me because I've been teaching for a long time. Oh, thank you so much, Cassie. I've been teaching for a long time, and every year I do 1/2 times 1/2. There's people that say 1, and it just breaks my heart. I know, you guys are in high school. You know 1/2 of 1/2. If I ask you for half a pizza, then I say, hey, give me half that pizza. How much pizza do I get? I get 1/4 of the pizza. I don't get a full pizza. half of a half is a fourth, right? All right, so half of a half is a fourth. So I'm going to have 1/4 pi. And there's 4 of those, right? 4 circles. So if I have all 4 of them, I have 1 pi. All right, so my probability then, oops, not probability, which you can write as P if you want, probability, is the area of those 4 holes, which we said was pi, divided by the area of the entire rectangle, which is 12. Okay, that's a number that is actually between 0 and 1. It may not look like it's between 0 and 1 because you're like, what's pi divided by 12? You can find it. It ends up being 0.2618. So what does that mean? It's around a 26% chance. All right, I wrote that, but I want you to write it like this. I want you to write 0.2618 or 0.262 if you want to do 3 decimals. Okay? All right, number 4. So find the probability that a randomly chosen point in the figure below lies in the shaded region. Okay, so you could find the shaded region by finding like the area of these triangles, but that means you're going to have to find this, and maybe they're not the same. I don't know if they're the same or not. Okay, so we could do the area of the rectangles, and we could subtract out those 2 trapezoids. That would work as well. Whatever you guys want to do. So I guess you could assume that these are equal. I don't want to explain why you can assume those are equal, though. Okay, so let's see. So let's do the area of the rectangle. Can you guys see this whole distance? 16. So we have 16 times 26. Can you hear me?
Yeah.
So we have 416. All right, let's do the area of the shaded. So that's going to be like our rectangle minus a trapezoid minus another trapezoid. Woo, that got crazy. That was not a trapezoid. Okay, does that make sense? Do you guys see what I'm saying? So our rectangle was 416. This first trapezoid right here. Do we think they're the same? What's the base, this base down here? 26. What's the other base?
26.
No? This base, I mean. Sorry, of the trapezoid, right? Remember how trapezoids have a base 1, base 2? So 10. What's its height? 8. Do you guys remember how to find the area of a trapezoid? 1/2 h b1 plus b2, 10 plus 26. All right, I actually have that twice because the other one also has 10 and 26 and 8 as its measurements. So I could just multiply by 2 if you want, right? Or you could subtract it out again. Whatever you guys want to do. I'm just going to multiply by 2. So as I start multiplying, I'm like, oh, that 1/2 and 2, that's lucky that I did that times 2 because it goes away. So I get 8 times 36. So I get 288. So 416 minus 288 is 128. That's the area of the shaded region. So they can get a little complicated. So the probability then is my area of the shaded region, which is 128, divided by the area of the rectangle, 416. Which as a fraction, you could reduce that out as a fraction and you could say, oh, that's 4 out of 13. Right? I did math 1, changes it to a simplified fraction. Or I could say 0.3077, around there. Around 30%, right? Does this make sense? All right, I'm going to give you guys your homework.